quick. We're about to start.
So our presentation is in Google Slides network.
Which one on network?
Sorry?
Sorry?
My presentation in Google Slides.
Okay.
Yeah, our
What is that?
meeting late this afternoon because we're just driving. It's just 2 hours. It's very close. Yeah. I just drove here yesterday.
So it's online.
Arrived here yesterday afternoon.
But the link.
Yeah.
So you have to have a link to
So it's very convenient.
Google Drive.
Yeah.
You go to the USB stick.
How do I do that?
From Urbana-Champaign down to downtown Chicago is 2 hours.
Oh, that's it.
No big deal. Yeah.
Simple slides.
Can I send you a link somewhere? Your email or something?
Yeah, I can take care of that.
Yes. Sorry?
I can take care of that.
And what are you going to do?
There's an email for this account
Oh, okay.
that,
Well,
you know,
we have, by the way, 2 minutes. No hurry. No hurry.
so email this account, SigmaPods 2017B. And I guess I can download it later if this doesn't get
Well,
done in the
yeah.
next 60 seconds.
Right. Well, the thing is that we are starting a session right after the keynote with 10-minute talks. So I would like to have it
Right.
on the not to do that
Absolutely.
while. So that's why I asked
2017B.
to do this beforehand.
So do we have all the 3 talks
At
that are going to
Gmail.
present it just after the keynote?
No, that's what he is trying to do.
He's the one.
He is the one missing. That's okay.
I've been invited to the HTAP survey.
Okay. Excellent. Okay.
How do we? Okay, so do I need to download this?
Yeah, download it.
Is this a Google slide?
It's Google Slides. So if it's possible to do it through here, that'd be great. Otherwise, downloading it is
I
fine.
can do that.
Okay.
No worries.
Good. Right.
Let's see if we can free up some RAM. I remove whatever this is.
Well, I think you can also, but you can also present it from the browser.
Not that one.
Okay.
Okay.
Sorry
Can you
about that.
try
No
to click real
problem.
fast?
Yeah.
Just try
You
to
mean-
click it real fast.
You can go forward like this.
Okay, let me fix that. Oops. Okay. Okay.
Okay. So good afternoon, everyone. So we're starting with the second, as in the post-lunch session of the workshop, and it's a pleasure to introduce Professor Javi Han, an able professor from University of Illinois at Urbana-Champaign, and we'll have our second keynote, which is titled "Construction of Structured Heterogeneous Networks from Massive Text Data."
Yeah, good afternoon. So, welcome to this session in the morning. I attended part of the session because I was in one tutorial. And so my talk mainly is about the construction of the structured heterogeneous networks from massive text data. In the morning, the session basically say how we take the network. It's already there. We take the network, we try to do network management, we do the mining, we do analytics, which is great. But people may ask one question is, where are those networks come from? Okay, so that's a very good question. The reason is, if you say where the data come from, actually the majority of data in the whole world now we call big data. The majority of data people actually claim is over 80% of the big data actually are in the unstructured forms. Okay, the unstructured form means they could be written in natural language, in social media, in image or something they're hiding somewhere in the tables. So those data actually quite unstructured, noisy, dynamic. But one important thing is they are interconnected. Okay, if you got one name, the other name, maybe they're the same person, you can connect them. Okay, so that means we actually need to do something to handle this unstructured data. And what we propose essentially 3 keywords. One keyword is structuring. That means we want to turn the unstructured data into structures. Okay. Then the second thing is networking. That means we want to construct the structured data into some kind of heterogeneous information networks. Then third one is mining and reasoning. Once you get networks, we need to analyze them. That's why we do mining and reasoning. That means if we want to do big data to knowledge, we call BD to K. Okay. Our proposed scheme is BD to N to K. That means big data, we want to turn them first into structured networks. Then we can turn the structured networks into structured knowledge. So that's the whole game. And that means actually the bottleneck is how can we get this heterogeneous information constructed, this network constructed from the massive text corpora, unstructured data. Okay. The first thing we want to argue is if we can construct such a network, it will become extremely useful. Okay, just give you, if you look at the pictures over there, okay, you look at the picture over there, you get PubMed data. How much you got? You get incremental number of research papers published, collected in PubMed every year is more than 1 million. Remember our DBRP is 2.some million, okay? The incremental is more than 1 million, okay? That many papers, do you think everybody has time to read it? No way, right? So the only thing you can do is machine, okay, using our computers to do it. That means we can extract from the documents various kinds of proteins, genes, disease, or treatments, and chemical compounds, all these things. We can link them, if we can automatically link them into massive structured networks. A lot of knowledge, you don't have to read it, machine can mine it for you, okay? So that's very interesting. I just show you one interesting study a few years ago we did is just took DBRP. That's the data we already have. And you construct the DBRP based on the authors, key phrases, and venues and the years and all these things. You construct it, just look at the title, okay? You can do something magic. For example, you can say, who are the leading researchers on web search? Okay. Or you can say, who are the peer researchers of Yuri Leskovec? Okay. Or you can say, whom will Christos Faloukas collaborate with? Okay. All those things you think is hard to do, we actually showed you really can do it. Just give you one example. Like a few years ago in Asenum 2011, that time that's a PhD student, Yi-Jo Sen, she actually published a paper saying she can predict the future co-authors of, say, Christos Faloukas. Can we do this? Okay. Actually, if you really look at the network in DBRP, you actually will find they are structured in a way you get authors, you can link to the paper may cite the other papers, the other paper may have authors. Okay. If you want to find the future collaborators, future co-authors, in principle is you want to find a future APA relationship. What you need is using those metapaths, you will find out which metapath is more important, more useful than the others. You will be able to construct something. I just show you. We took this data, we actually did some experiments, you look at those different metapaths, those things we mark as 4-star. It's like 4-star hotel, yeah. Those 4-star paths actually is a very useful path. Just give you a simple example. You look at the APVPA, that is the sheer common values. They both publish in Sigmund, okay. You can say APAPA, that is the sheer common co-authors. They both co-author with, say, Mike Stonebreaker. And there's APTPA, that is they share many common terms, right? They both say deep learning or something. So, and the last one, I would say, they both cite same papers, okay? Those are the high quality 4-star metapaths you can use, okay? Then you can predict something. We actually showed, like we took Jian Pei, who actually was my PhD student many years ago. We predicted from, because he got a PhD from in 2002, we want to predict 2003 to 2009, who will be his new co-authors. That means we hide all the later data. We just took 2002 data and before. We try to predict what are the new co-authors in the next 6 years. And the prediction accuracy was pretty good. You probably see the top 5 ones, 4 of them were true, okay. The only one was not true is Osma Zayan. Actually, Osma was my PhD student. They were sort of like schoolmates or teammates, but they overlap partially. Actually, I was asking at the KDD conference, I was giving a keynote in 2012. I was asking, what happened you never collaborated with Osma? Okay, he actually stood up. It was a little embarrassing, but he said, actually, your data was not, you finished in 2002. We actually had a co-author paper in 2011. Okay, that means our prediction was not too bad, right? So that implies it's a little amazing we can predict those people even in the next 6 years, but it shows some power, right? So then the question becomes, okay, we can have magic power if you really construct it, reasonably complete, less noisy, heterogeneous information networks. But the major question is people do not put in the structured heterogeneous information network that much information. What you really see is people see the massive corpus like news, CNN, every time you turn on a TV, you see something, okay? And those things, can you automatically construct a network based on those massive text corpora? Okay, that's a major problem. And after Izhou graduated, we got a major team. We said, we have to solve this problem in order to make the heterogeneous information network really magic. We have to solve from data to network problem, okay? Then the problem we got is, we got a massive text corpora. We don't want the people substantially doing curation and labeling because it's just too expensive, okay? But we do have a knowledge base, like a Wikipedia. And what about we take the general knowledge base, take unstructured text corpus without human effort, whether we can extract the key phrases, getting typed entities, then we construct heterogeneous networks, then we derive knowledge. You can see the whole flow graph is very natural, right? You get unstructured data, you want to turn them into networks, okay? Can we do that? Okay, so actually after Izhou graduated, we actually work on almost 4 or 5 years, working on several major things we think we really can do, make some good progress. We like, the Sigma people can absorb something because we publish in a KDD, even EMNRP, those natural language processing forums or many other forums. We want you see the light, the structured data is possible from unstructured data. Then our database game, play with structured data, is still valid, is still powerful. Okay, can we do this? I'm going to show you phrase mining, entity resolution and typing, relationship discovery, metapath. All these papers are already published in many different conferences, other venues. But I'm showing you one by one. It can be done. It can be done nicely. Okay. The first thing I want to show you is phrase mining. Phrase mining means you come down to see a very massive corpora. You want to turn this massive corpora into structured networks. The first thing is you have to figure out what is the integrated semantic unit. Okay, if you use a different language, you may say the minimum semantic unit, like in English, you start with every alphabet, A, B, C, D, it doesn't make any sense. But even you take the word level, it still may not make too much sense. I just give you example. Suppose we say United, okay? If I go to airport, I say United, you think, oh, that's United Airlines. But what about I go to United Nations, I say United? You do not know United Nations or United Kingdom, United States, or United Postal Service. There are so many United, right? So if we know this, we have to get a bigger one. We call phrase. Then it will make sense. You get a real entity. Okay. So we did this just taking either nothing or some very minor labeling, or using wiki or things like this. We actually got a quality phrase extracted automatically. And we got several papers, including VRDB paper, including Sigma two years ago, and the new paper actually just like published as a book chapter. So I probably can show you some very interesting things. The first important thing is you do not need training, but you need a little statistics. Okay, what statistic you know? The simplest one. You know the normal distribution. Okay, you just need to know that you can understand this. Why? Okay, you think about this. Suppose you came from Mars. You know nothing about English. You know nothing about computer science. Okay, now I give you 2 million DBRP titles. Okay, one title said Markov blanket feature selection for support vector machine. I read this, you can understand it. How about Martians? Martian will reason why support vector getting together is a phrase, or supporting vector machine getting together is phrase. You have to give me reasoning. Okay, fine. Suppose this Martian is a very fast computer. Okay, what you can do? You just count. Okay, you count. You get 2 million titles. You count them. You will say, oh, support is a frequent word. Okay, vector is a frequent word, but even it's frequent. Support, suppose, is 1 over 1,000 frequency. Vector is 1 over 1,000 frequency. Support vector getting together. What do you expect? If they are random, they have no relationship, 1 over 1,000 times 1 over 1,000 is 1 over 1,000,000. I got 2 million titles. I need to see support vector may occur only twice. But if I really count it, they occur much more times. Okay, what I can explain? I say it's far away from standard deviation. Okay, how far? If I'm 3 standard deviation away, the chance is 0.3%. Now you can see I'm 12 standard deviation away. What's the explanation? They glue together, right? Glue together means they are phrase. Okay, that's what Martian can find phrase, right? So if you think about this, support vector getting together 12 standard deviation away. Even the add machines, they're still 8 standard deviation away. They are very good phrases. I have to take them. Okay, so that's exactly this method. It's language independent. You go to English, you can do this. You go to Spanish, you go to Chinese, they all work well. Okay, so if you know this, now we get into our standard. The standard is we use popularity. That means more frequent, like information retrieval is better or ranked higher than cross-language information retrieval because it's more frequent. Okay. The second one is concordance. That's why they glue together. Okay. You probably see. You see strong T. How many times do you say powerful T? Okay. You see powerful computer. How many times you say strong computer? Okay. Then you know something can glue together. They're concordance. Okay. That's a concordance. Then informativeness means if it's too frequent, like off or the or something, it's just a stop words. This is just a stop phrase, like this paper. Doesn't make too much sense. Don't rank them high. And completeness means you get vector machine, but almost every time you get a vector machine, you also get support vector machine. That means actually this one is not independent. The complete one, support vector machine, is independent, right? So you based on this one, you can easily rank. Even Martians can rank, DBRP very nicely. And we actually tried this. The interesting thing is everybody knows topic modeling, and David Bly, who is the inventor of topic model, okay, he came last year. He visited our computer science department to give a, invited keynote, invited distinguished speech. He went to my lab. I could show him just the slides. He got very surprised. Why? You can see this. We got, from Europe review, we got like several hundred topics for Europe. You look at this, okay. This one is we do not have any annotation knowledge or curation or anything. We just do the phrase mining, then we run his revised NDA. Okay, we got this. And you see this part is more like McDonald's, right? It's kind of a Western fast food. This one actually more like Chinese food or Asian food. Okay, then you find all the others like Mexican food. You can chips and salsa, rice and beans. You can see this very nicely topic modeling. Okay, what you can do? First do phrase mining, then take the phrase mining into topic modeling. It will make a lot of sense. And that one we did not use any training. But if you put a little training, say this phrase generally, I really love it, that one is not good. So we put a little one, we can kick in the classification modeling. Okay, if we do the classification modeling, we can do better. I can show you this one is just from CKDD. We have something on Sigmod as well. You probably can see we got time series, gene expression data, frequent subgraph, category, attribute. Those red ones is we find it the typical like Stanford name chunking entity, those name chunking algorithms, they cannot find this ranked high. But they rank something high, like those blue ones. We think they are common sense. We do not rank them high. You probably can see it does make sense, right? And what about people do not even want to give you a label? And you do not want to say, I do not train at all. I still want something to train. Where we can find the training data? Wikipedia. Okay, you just think about it. Suppose you want to read, find the phrases for Spanish. There are Spanish version of Wikipedia. You can use. Let's look at the English one. Okay, the English one, automatically free. You can get lots of good phrases like Barack Obama, Anderson Cooper, U.S. President. Those are the phrases which are very good. How do you find it? Because those things they have the anchor, links. They link to the page of Barack Obama. So you can either say, oh, this must be a good phrase. Otherwise, why get an anchor page linking to this entry? But not everything good are anchor page linked. Just give you a simple example. Obama administration. You go to Wiki, you find it. There's no Obama administration as anchor link. It's a good phrase. So why not? Now you have Trump administration, right? So, but they are good phrases. It's not in Wiki, okay? So what we do is positive pool, very big, because we have a wiki. But negative pool, very potentially big, but it's noisy. Because Obama administration is a possible one you put in the, because you cannot find in the wiki link, you put in the negative pool. So we actually did a study. We have 100% good, very big positive pool, but we have, for this negative pool, we have 10% non-trivial, 10% noise, okay? So how can we do good training? Actually, we develop a method. It's very smart in the sense, positive pool is 100% great. Negative pool, 90% great, 10% no great. But we don't know which 10%, right? How we can do this? Remember, we have those random forests. We can do ensemble. You think about it. If you got a perfect positive pool, only 10% mixed negative pool, you can do ensemble. You just ask them to vote. Okay, you're thinking if you train 10 classifiers, you ask them to vote, they will wipe out those not good ones. Okay, so we use this ensemble doing the random forest to vote. We actually got a very big training data, not 300 labels. We have 100,000 labels, and we have so many good data sets to train our one. Okay, and the accuracy is very high. I can show you. You can see we use DBRP, YERP, English Wikipedia, Spanish Wikipedia, Chinese Wikipedia. We actually show the data set is really, really in the multiple gigabytes. And you probably can see those are one line is English, one line is Chinese. Anybody can read Chinese, you probably can see those are the, even you get 100,000, things, they still get very high quality phrases, okay? And Spanish we also showed. We actually have a Russian student. We actually asked him to judge whether Russian is good. Is also very good, okay? That means you get anyone's Wikipedia. The only thing we do not really have is some small tiny language, only several thousand people using it. We don't have a wiki, okay? Of course, it's still a very good research question. You can make it. But you probably see those TF-IDF and everything, the accuracy is very high. Once we can get phrase, another important thing is whether you can type those entities, those phrases. Type those phrases, just give you a simple example, okay? Suppose you get a Yelp review like this. The best barbecue I've tasted in Phoenix. I've had a pulled pork sandwich with coleslaw and baked beans for lunch. Okay? You got this. The Earthlings can understand this very well, okay? What about you get somebody came from Mars, they can't understand what's going on? Okay. You have to understand types. Like the barbecue, BBQ, actually is not a machine you can eat. Okay. It is the food you can eat, right? So Phoenix is not a bird, but it's a city. So how can you know this? Okay. Even you have a dictionary in hand, it's not that easy, right? So you have to actually really doing some kind of typing based on your context. Okay, so that's the one. Actually, I have a Xiang Ren actually sitting here. That's what he developed in the last several years. Got lots of papers published, and he did a tutorial in the morning on this as well. So the general philosophy is this: we have large corpus. We don't need any human to do labeling, but we have a wiki. We have a phrase base. Phrase base already give you types. Say Obama is a person. Okay, U.S. is a country, or something like this. And we have something, but don't trust they have everything. Actually, we checked. Overall, if you get a New York Times, get a Yelp, get a Twits, we checked overall. If you randomly pick one, you want to find whether it's in the phrase base, the chance you can find is about 7%. I mean, 93%, they're not linked. You have to do something, okay? And how can we do it, okay? The general philosophy is something very tricky in the sense even you find it in your place, they are multiple sense. In the sense, Washington, okay? For example, you look at Washington, sometimes this Washington actually means a government. Sometimes it means a country, sometimes it means a state. And some case like this, some actually is a sport team, like team in Washington, okay? In Washington, D.C. Okay. So how can we know in this sentence or in this article, it means it's a sport team, okay? Washington versus, say, like Portland, okay? Actually, it could be Washington. Actually, is a Washington D.C. It's not really, Another interesting thing is based on the context. The context itself is very sparse. Okay, just think about this one is about the Japan tsunami, okay, earthquake, tsunami, and nuclear accident. If you look at the sentence, they mean the similar thing, but they have so many ways to say it. Okay. Can we automatically cluster those things, cluster different ways to say it? We say the right-hand side must be a location or something like this. Okay. So what Xiang actually did was this. He actually took all the different, surface names. He links to something you can find. Okay, either in the wiki or not, or you can see actually there are relationships like this. This is a relation phrase like has office at, is ally of. Different color means it's in the right-hand side or in the left-hand side. Okay, that means whether it's in front of this relation phrase or after it. And you take this, you with multiple types, you construct these networks, and then you can do reasoning, clustering, and propagation, okay? So I'm not getting into the very detail, but the first thing is you take those things, verbs, okay, the prepositions or these things as your potential relation phrase, okay? Then you have the nouns or the other parts, you actually can connect them, okay? Then what you do is you have something in phrase base. You know some types. You know Obama actually is a person. You know this, you do the type propagation in this heterogeneous graph. Once you propagate, those relation phrases can be clustered. Okay. The cluster one can go back to make the type better, and you can cluster better. You turn them into loop, into optimization. Actually, things can be done far better. Those optimization, I'm not going to explain in detail, but what you can see is this whole objective function can be partitioned into 3 optimization procedures. One is on entity mention modeling, the other one is on type propagation, this on multi-view relation phrase clustering. These 3 things working together, you can get a really good results. So this one actually shows we can compare with even Stanford NER, which is very popularly used, okay? And it's curated in the sense people put the label there. We do not have any curation, just use phrase base. You probably can see the result. New York Times, Yelp, and Twits, you can get better, okay? So there are lots of things to be done, but I can show you something really interesting is you want to find a good type. You need to cluster those relations. And how do you cluster them? You probably can see. That's one I gave a talk in the ACL, it's a computational linguistic. I give a keynote. Actually, some good scientists, they raised question, challenging me. Said, you cluster those 3 things, recruited by, employed by, wanted hired by. They actually means different thing, because wanted hired by means you haven't hired them yet. The employed by is already there, okay, which is true. But the interesting thing is we're not trying to say they have the same meaning. We just say the right-hand side, they have the same type. The type recruited by, employed by, wanted hired by. That part is our employer, okay? That's the one we want, okay? That's the one we do the clustering, okay? The result you can see is pretty striking in the sense we compare with many NLP people doing this, like from Stanford, from University of Washington. Those are very well, published and also open source. You can play and test it. And this one we also made it open source. Anybody can play with and test it. But you see, those are the 100,000 New York Times articles, Yelp, and Twits. We all can do better. Okay. And also, a very interesting thing is not only you can do better on the top type, like we call rough type, like person, organization, location, those things. But also you can do refined typing, just to take Donald Trump as an example. Look at different sentences. Actually, you get different types. Everybody agrees Donald Trump is a person, okay? But that's a rough type. You want to go down, you will see Donald Trump sometimes in some sentence is a politician, but some sentence is an actor in reality show. Sometimes it's a businessman running a company, okay? At the different parts, you want to type them correctly. It's not easy, okay? The general game is you have to look at surrounding sentence. Then those sentences, you have to do a little embedding, mapping them into correlated things, okay? The general philosophy could be this, okay? Suppose you got Hillary Clinton, you got Donald Trump, okay? You find Hillary actually mapped down to something only to politician, the part. But Donald Trump actually, some part mapped very close to the space with Hillary. But sometimes he maps something actually to the business part, okay? Then you probably say, this part actually means Donald Trump is a businessman. The other part means Donald Trump is a politician, okay? So that's embedding actually play a very important role. We do have a few papers on this embedding, but with the time, I will not get into detail. But what you can see is embedding is very powerful, okay? With this, you probably can see we have the most recent one is the W 2017 paper, is this one called code type. You probably can see this code type one with embedding with this one, you can get a really high on the F1 measure compared to the others, okay? But anyway, you probably can see there are lots of interesting things ongoing if you want to turn the unstructured data into the typed data, okay? Then another thing is, with network embedding, we also can do relationship discovery. The relationship means you really, really want to find some particular specific relations with massive amount of data. Just give you an example. You go to PubMed, it's millions of articles. Can you find the particular relation between gene and disease, gene, drug and disease, drug and pathway, those things? For example, the first important thing is you have to recognize phrases and entities. For example, non-small cell lung cancer. Actually, this looks very long, actually just one disease. It's one phrase, one disease, okay? Then can you find what's the drug or what is the symptom or genes linking to this non-small cell lung cancer? Actually, they were all in PubMed, even in the abstract, you can find them, okay? So the key thing we did was, the first thing is phrase mining. You get entity. The second thing is, based on this phrase mining, you put them in the network, you do the network embedding. Okay, with this, you can calculate the similarity. Okay, just give you a simple example. You can give one example, say, BRCA1 and breast cancer. Okay, actually, I think the person who got this BRCA1 linking with breast cancer got a Nobel Prize, okay, many years ago. But what you can see is you have a gene, you have a disease. They link together. Okay. Now you go down to PubMed. What you want to see is what others. If you give me another gene to say what kind of problem it links to, or give me the problem, say what a gene links to. Okay, so those things you can, based on the embedding computation, they actually, if you map them, they have the parallel vectors in the low dimension space. Okay. So the detail, I will not get into this if you know the embedding, but I just show you, we randomly pick, not even the last 10 years, randomly pick up top, just a 10% PubMed abstracts. And probably see, it becomes a little magic. You put breast cancer and BRCA1 as one training data. It's like a one sample. Now you can ask me, you say, acute myeloid leukemia is on the left-hand side. The right side, it should be what? We immediately show you, not BRCA1 anymore. Those are a bunch of genes. They link to this problem, to this leukemia problem. And you reverse it. You say, now, I give you a gene, what's the problem? Now, you give me a gene, those are the problems, okay? You can get a drug. For example, you can say, doxorubicin and leukemia linking this way. Now I give you aspirin. What are those other things linked to? Actually, we found aspirin linking with ulcer bleeding, and the other one. Actually, these are two different functions. One is you use aspirin too much, you get ulcer bleeding. But why you use aspirin? Probably you want to cure some kind of heart problems. Okay, so you probably can see they have both functions. You can link them together. And we actually got into UCLA people interested. Their heart center at UCLA Medical School, they actually give us a task. Say, now they have 6 different kinds of heart problems. They say, you give me this, you want to find the other parts, actually are the drugs, like this, aspirin. This is a heart disease aspirin. You want to find drugs, or you want to find genes. So actually, those things can be found, just running the same procedure. Okay. And those are the things you actually can find. Different heart problems, these are the top-ranked molecules, only dedicated to this heart problem, not to the others. Okay. Or you say, ranked very low to the others. Okay. So it becomes very, very useful. Actually, one physician in UCLA Medical School, they actually said you found something, a new cure. Okay, what is new cure? The interesting thing he explained to me, I originally didn't know anything, we just showed this, ranked the things. But they say, there's one problem, I forgot exactly the problem. What he said is this rank number 1, linking to this, every physician knows. Okay, they treat on this. But rank number 2 and 3, not obvious. Why? Because remember, there are many, many proteins. They link to every heart problem, not distinguishable. And they don't want to see it because they cure, you get this heart problem, and you look at those proteins, there are several proteins, they show all the heart problem get this one. Okay. They don't want to see that. They want to see specific one, just dedicated to this one, not dedicated to the others. Okay. We identified them. They actually, the physician said, there's one group of people are the children. Okay. If you check, the number 1 problem is for adults. But number 2 problem, very likely to be children, because you treat this number 1 protein, there's no response. Okay? And they don't know how to do it, because they don't know which protein to train and to treat. And now we found those ranked dedicated proteins, they really love it. Okay. And the last one I want to show you, the technique, is MetaPad. We just got this paper accepted in the KDD 2017 last week, or this week, I should say. Yeah, it's this week. But I probably can show you, it's very exciting, is this, okay. We got massive text data. You want to automatically extract things with this, okay. You want to get an entity, attribute, name, all these as a structured pairs. You want to extract them automatically, okay. Remember, human can do this because you have lots of things in your mind. You're smart enough, but not computers. I just give you one simple example. You can see how computer get difficulty, human can do it, and how computer, now we can do it, okay? Give you one simple example. There's one sentence called, President Brass Compaore government of Burkina Faso was founded something, okay? That's in the newspaper, okay? Or in the wiki. Anybody know Burkina Faso is a country? And this Blaise Compaoré is the president of this country? Nobody knows. Actually, even in the very massive newspaper, it only occurred once. Okay. And how can we get this entry extracted? And you not only extract it, you are very confident this one is right. Okay. Can we do this? Okay. The interesting thing becomes this. How can we, based on this, is there any pattern similar to this? We can get it. Actually, there are lots of similar things. Just you change the president Blaise Compaoré to Barack Obama. Okay. Then you change the government of Burkina Faso to government of the United States. You will say, oh, I see it in newspapers so many times already. Okay. You can see they share same pattern. We call meta pattern. Okay. You get this meta pattern. If you can extract the meta pattern, cluster them, you'll be very powerful. Even they occur for this particular country. They only occur in your newspaper once. You can get it unambiguous, confidently, you know it's right. Okay. So you can see the game is this. Okay. We want to extract this, but this some happens so rare. How could you guarantee you extract it right? Actually, what you want to extract is the type level. You can see, if you can extract the country president, country population, person age, you can do this, you could become hero, okay, just by reading newspaper automatically, okay. Actually, those things people have been trying, okay. Give you one simple example. Stanford OpenIE and Allen Institute of AI, they are doing this. Another very important thing is Google. Invested lots of time trying to do this. Google's project on Bipedpedia, Renown, all these published in WWW, in EMRP, they are doing this. They have a big team working on it. Unfortunately, Alon just left Google about a year ago. He was leading this effort, actually got lots of papers on it. But the difference is Google has massive query logs. They basically rely on query logs to find those patterns. But we don't have query logs. We don't like a Google, we have no query logs. Okay. Can we do this if we have massive newspapers? Can we do this in the same quality or even better? Okay, that's the question. Actually, this question you can see you can overcome it in this way. Okay. we look at the first one. This one is hard to extract. But if you can extract the types, remember we can do typing. Okay. If you can extract types, you will find this one actually has the exact same type as the President Barack Obama's government of United States claims something. You see the newspaper, it happens many times. Oh, you say that one happened not that many times. Did you see US President Barack Obama something? It happens and not now, but you see it every day, but now you change to Donald Trump. You see it every day, right? So if you know this is a pattern, okay? If you can extract the pattern, it happens so many times you can extract it, you can make it right, all those information in the newspaper are digestible and can put in a database, okay, because they are structured data. You think they are not structured, they are structured if you can do this. Okay. So the key becomes whether you can extract this pattern as a meta pattern, or you can even extract even more general pattern. This is more like a summarized one. Then you can go back to extract newspapers, whatever you like. Okay. So this one, actually we did this, is based on this. You turn the phrases into meta pattern, into types. And for these typed pattern, you play the same role almost. You use frequency, concordance, completeness, and informativeness using this. You can get rid of those not high quality patterns. You can get a very high quality patterns using this as a meta pattern. Okay. Once you get a meta pattern, you actually can cluster them, group them into similar ones. Semantically, they are synonyms. They are very similar. For example, you look at this. Country, president, politician. You look at this, you have present there as a common keywords. They occur with the same country, same politician so many times. They essentially can merge them. Okay. The interesting thing was this. I was working on NIH project. Stanford, Mark Musin, they're doing a big project. The project, one project is they force people to enter the data in a standard way. Okay, just think about your age. Okay, there are hundreds of different ways to say your age. Okay, and if you don't say it in the right way, how the medical doctor, the researcher, can just read what the physician written, can figure out what exactly your age. Okay, actually, you can see these are different ways to say the same thing, and we can actually easily, based on the meta pattern, we can cluster them, you will get it, okay, automatically. You don't need force people to enter in the right form. Nobody wants to do it. Another interesting thing is get pattern, which level the pattern should be. For example, you can see, you look at the age should go as high as a person, okay, or even animals, okay, you can go up. But those are the very high. But if you look at a country president, you don't want to go to person because not every person is a country's president. Right. So you only need to go to a certain level. So we actually, based on the distribution, we can either figure out, based on, you plow through your corpus, you actually can figure out which level should go for this pattern. Okay. With this, you can see something pretty interesting is we use the New York Times, we go down there, you can grab those are the entity of the country, those are the president of the name, big or small, you can get it right. The same thing, you go down to the company CEO, you actually can get it right. Okay. You can see, you can extract those facts. Okay. And you go to the medical literature, you can get something pretty magic. For example, you can see this one said treatment was used to treat certain disease. You want to find disease and treatment. You use those patterns, okay? Those patterns automatically generated. You actually can find different disease, different treatments. Going down to PubMed extract, you can grab this, take no time, no cost, you can grab this. Okay. Same thing, you say this bacteria was resistant to certain antibiotics. There are so many ways to say it. Once you figure out, you go down to the PubMed, you can extract a certain bacteria was resistant to certain antibiotics very easily, very quickly. So, and also accurately. With this, we got very excited. Actually, Xiang leads a team. We go to PubMed. We say we want to construct structured biomedical networks. We call LifeNet. Okay. With this, he actually got in. Those are the things you extracted. So you can see type is disease, like breast cancer. Those are the genes, proteins, and drugs, and all in different colors, they link together. Okay, you can see those links where it makes sense for physicians. How much cost you get? Okay, he compared a little on the cost. You'll probably see this effort is lots of physicians working together. Took 2,500 man-hours. They got this extracted. It's 2,000 facts extract from the biomedical literature. Okay, and this one is basically he ran his computer 1 hour on single machine. He can get that many entities, that many relations, that many more facts extracted. You know, the accuracy, of course, this accuracy so far is only 61%. That means there's a last room. It's not like research is dying. It's not far from dying yet. We want not 61% accuracy. We want to get 99% accuracy. So there's a long way to go. But the light is there. The tunnel is through. Okay. So we need to enlarge it to make it. Okay. So what my basic information I want to pass is you can see there are lots of things can be done. But the major game is we are facing big data. For database people, we know we can play well with structured data. But you have to face the real world. The real world is largely unstructured. Okay? You have to deal with them in order to show your power. Okay? The power, what we got is you need to dig through those massive data, let themselves behave by themselves. Not like a human, take every piece, try to give labels. Okay? What we do is, you can see, you do the phrase mining, you automatically grab from the text to get phrase, you do entity resolution, typing, and you do relationship discovery, you do the metapath, you generate the patterns. Finally, you can do something really magic. Okay? So that's the story, that's a lesson we are learning, but we think we want to share with our database researchers because I was in database research very deeply, but later I transferred by and by to data mining. But actually, database and data mining are very closely related. What we really want to show you is why we want to do data mining. We want to handle those unstructured data, okay? Because the structured, you get into nice records. We can do it. But the problem is people talk. They don't want to put in the record, okay? You have to do it by yourself based on the engine we can develop. Yeah. If we can do this, then we can claim the database people is not just working on structured data. We are working on unstructured data as well. Okay? Then we can turn the unstructured data into structures, into networks, and finally we can turn them into structured knowledge. Okay? That's the lesson we learned. And if you look at the whole evolution path, you probably see the early year 2000, I got this data mining textbook. Then later we look at the link mining. Then I got like one PhD, Yi-Zhou San. Now she's a professor in UCLA now. She got a dissertation award on mining heterogeneous information networks. Then I got a Chi Wang now in Microsoft research. He first crunched down into mining latent entity structures. Got a dissertation award in KDD in 2015. But we got a new book just published 2 months ago, is phrase mining from massive text and its applications. We do by and by. We work on the phrase, work on the types, work on the meta pattern, and finally we want to conquer it. We want to get into the finer, word is turning everything into structures. Okay. So of course we got lots of support from many sources, including NIH, NSF, like Army Research Labs, and many industry partners. There are lots of new research papers published. If you like, I would suggest you can, both, research papers and their associated codes. Their associated code are all open source. You can download, you can play with them, okay? So that's a nice thing. We just say every student, you have to put it on the GitHub. So they basically put on the GitHub. And A lot of industry people, they download it, they love it. Okay, for example, phrase mining. The same month we published in Sigma 2015, the same month in June. Actually, we got the YERP Dataset Challenge 2015 grand prize because we show the YERP data can be automatically identify the phrases. They love it. Same year, TripAdvisor sent us email, said that they actually put our software, they check so many different software, they put ours together with embedding. They are using it in TripAdvisor. Okay, so you can see things can be automated. You don't need to hire hundreds of people to do curation. Okay, so I'm ready to answer questions or join any discussion. Thank you.
We'll have questions.
Yeah.
Okay.
Yeah, thank you for the excellent talk. So you showed very nice examples, but like for example the Burkina Faso example or other ones with the genes and the proteins, but you get also many garbage data, and you need somehow to have threshold to say, oh, this is valuable and this is not valuable. So how do you determine the thresholds?
Yeah, actually it's a very good question. Of course, our software, including phrase mining, typing, including this one, we need some threshold or some parameter. The first important thing is the parameter actually is not very sensitive. Just thinking about the phrase mining. Okay, phrase mining, the key parameter, actually, I just show you about standard deviation, right? You say 3 standard deviation is something actually is very rare. Okay, 3 standard deviation away. Of course, you can set standard deviation to be 10. Okay, it could be even more rare. But actually, you get 2, you get 3, you get 4. Actually, it does matter, but it matters very little. It's very easy to set. Okay, the same thing as support threshold. For example, you say those phrase mining, you set support, you say support is 30. You actually can get very high quality phrases. But you say support now is 10. Actually, the 10 one can solve if your document is very small number. Okay, then you actually can get quality ones. It depends on how big your corpus is. But like this meta pattern, we also use, if you see the philosophy, we use same philosophy like this. This needs some threshold. Actually, the threshold is not sensitive. It's very easy to set. And based on your application, for example, if you use different language, like Chinese or Spanish or German, you probably need different thresholds. But you can play with it. You can set up pretty easily. It's not really like certain threshold you minorly adjust it, doesn't work anymore. Actually, of course, things can be more automated. That's also why we use wiki, because a wiki, actually you get training example, it's 100,000. And make your original training set, like 300 labels. The original 300 labels is somewhat sensitive. You give me very poor label, I probably can give you very poor results. But now the wiki, you get 100,000 as training example, it's not sensitive anymore. Okay, then you always get good quality things. Okay, yeah.
Any other questions?
Yes, yes.
So there is the RDF data. I didn't hear you talking about it. There is a big corpus about it. Does it get into your research in a way or the other?
Yeah, actually the structure is really dependent on what you want to capture. Like those RDF data, essentially it's like triple store. Like you have 2 entities, in the middle you have a relationship. You have entity 1, relationship entity 2. That's a typical one. But remember, you may want to add a lot of conditions, a lot of sentiments, or searching, or confidence. There are lots of things you need to patch up. So we can say the data, we are not exactly using RDF like triples, but you patch something which is somehow not too far away, just for your implementation convenience. I think if somebody strictly follows certain data structure, actually, this one you can easily year down to those structures with certain program efforts. So it should not be a major hurdle. You work on different structures. Okay. Yes?
Can you combine this pattern mining with maybe want to improve the accuracy with the fact that you have doing this continuously on a continuous basis so that you get some new events that happen so that you can take advantage of things that happen now currently?
Yes. Yeah. Peter just said about whether we can do it in a continuous way or in an incremental way. Actually, all these design, the first thing I should say, there's still lots of room to improve. For example, not every meta pattern we got is 100% accurate. So there's a, we call truth finding problem. Simply says you need to actually incorporate some truth finding methods. For example, who said this, or which curation routine, or which routine you get this, how confident this pattern is. There are still lots of things to do. And incremental one, in principle, all these can use incremental one, but which knowledge, like a newer one or older one, if they conflict in each other, how do you judge? For example, who is the president? You know now it's not Barack Obama. So you get a conflict one, actually, even you get a majority corporate said Barack Obama, a small number said Trump. But if you like timestamp, you will know actually even the later one, the minority could be the winner, right? So there are lots of such things need to be incorporated into the whole thing on the knowledge-based construction. But this just first give us a skeleton. Okay, we can put a lot of new stuff inside to enhance it. Okay. Okay, yeah, thank you.
Let's thank you, Peter. So we'll now be moving to the grades talks, and I request Peter to, take the stage.
Yeah, thank you, Akil. So, after this very interesting keynote, thank you again.
Thank you. Yeah, I should give you.
We're going to accelerate in terms of talk size, which is restricted to 10 minutes, and I will have to be relatively ruthless. So please stay within those time limits, otherwise not everybody can speak. So our first speaker is Konstantinos Xirogianopoulos, if that's correct.
Yeah, that's pretty good.
Pretty good, okay. So take it away.
All right, so let's see if I can. All right, hi everybody. My name is Konstantinos. I'm a grad student at the University of Maryland. And following up Dr. Han's great talk, I'll actually talk about how we can leverage data that's very structured and stored in relational databases to do graph analytics. So I'd like to talk about our system called GraphGen and our ambitions towards providing adaptive graph processing using relational databases. So this is a graph data management conference, so I'm sure all of you are convinced that graph data is awesome and it's really useful. And it's been used to provide analyses that are valuable in many different domains. And there's many different systems that people have been using to manage their data. People have been using graph databases based on their workload. People choose to store their data in a different format and use distributed batch analytics systems, in-memory systems, and other different systems. In particular, there's a certain kind of work that is focused towards actually combining graph analysis with relational databases. So most of these systems actually focus on ingesting a graph that already exists into the database, into nodes and edges tables, and basically delegating the entire graph analysis task to the database itself. What we're trying to do with our system is we're building a system that actually enables users to declaratively define what kind of graph they want to analyze on top of an already existing relational schema. and to basically enable them to extract that graph and efficiently be able to analyze it right off the bat. So what do I mean by extracting a graph from a relational database? Here we can see an example from the TPCH database. An example graph would be, let's say, a graph of where the nodes are customers and they're connected to each other if they bought a common item. So to do that from a relational database, we'd first need to, for example, figure out which customer bought which product, and then on that result, we'd need to do a self-join to figure out which customers bought the same item. And that would actually give us the edge table that we need in order to analyze this graph. And as a matter of fact, there's many different types of graphs of potential interest in databases like these. And so enabling users to actually be able to easily define those graphs on top of their schemas and right off the bat immediately be able to analyze them is something that would essentially open up graph analytics to all of the data sets that are stored into such structured databases. So quickly, our system basically is, the way that our system works is the user basically defines a declarative definition query over our system. Our system extracts the graph that the user wants to analyze in some way, shape, or form. And then the user defines an analysis over that either declaratively or or by writing a program over it using either a vertex-centric framework or basically a program over the graph itself. And so I'd like to quickly go through the language that we have to define these graphs. We have a declarative language based on data log loosely, which allows users to define what we call a graph view over the database. So here's an example of a graph, of like a co-author graph from the DBLP data set. So here the nodes are defined from the author table, and then the edges between those nodes are defined if they've published a common paper. We could do things like aggregate edge properties over these to, for example, have an edge property for the number of publications. And another thing we actually want to do is define collections of extraction of various collections of graphs over the database. And we can enable many optimizations over those, which I will talk about in a few slides. So this is an example of basically extracting all of the ego graphs from this co-author graph from the DBLP database. We also want to enable graph querying over these graphs. And there have been many languages proposed like Sparkle, Cypher, and PGQL that people have been using for a long time. And so we want to support those languages. But another natural fit here is also Datalog, which is really good for expressing recursive sort of computation over the edges view of a table, of a sort of graph. And so this is an example of a one-liner that would basically just give you all of the triangles of authors whose areas follow this specific pattern. So one works in ML, one in DB, and one in algorithms. So the main idea here is that there are many ways that you can analyze these graphs that you may want to extract over relational databases when those graphs don't explicitly exist. So you can either extract the graphs and do it in memory, or you can give the analysis to the database. And the goal here our goal here is we want to actually adapt the execution based on the analysis, based on the query, and based on the workload. And the purpose of this paper is actually to define what the challenges and opportunities in doing something like this are. So, of course, when trying to define where to execute a graph analysis query or task, it depends on many things, right? And as you can see in this table, this is a triangle pattern matching query. So as you can see, running this query in memory is very fast versus running it in the database. But if you actually only want to analyze this once, so if this is just a query that you want to do one time, then the ETL required to actually extract the graph and load it into memory is significantly higher than just handing it over to the database. So the key challenge here is to develop accurate cost models, tools, and techniques to enable you to figure out where to do that. Some other issues here include large output joins that come out of the extraction of these graphs that we've talked about in our talk at SIGMOD a couple of days ago, as well as selectivity estimation errors associated with these complex joins. So second thing is, let's say that you decided to push the query to the database. Then there are many different types of ways that you can actually translate these declarative queries into SQL queries. These automatically generated SQL statements are often very challenging to optimize. So there are two different ways here in which you can define a graph, let's say, as SQL queries. One of them is using a with clause. One of them is using a database view. And there's also different ways to do duplicate elimination. You can have your distinct clause in the edges clause, or you can do it afterwards. And as you can see here, even though you would expect that the query optimizer would figure this stuff out, there's mass variation in terms of performance with all these different ways of actually writing SQL to extract these graphs. Lastly, we want to optimize over extracted collections of graphs, and this is actually very useful for doing things like ego graph analyses and analyzing snapshots of graphs. And so the ability to refer to each of these graphs independently can lead to significant savings. And so the challenges here are basically, how do we develop a systematic approach for optimizing the extraction and the execution, both of them, of these sort of collections of graphs against the database? And we actually started working on this. So if we take the example of ego graph analysis, then so the naive way of actually extracting multiple graphs from the database would be to generate a separate SQL query for each of these distinct graphs, and give all of the queries to the database in sequence. We've actually come up with a method called result tagging that we can use to extract all graphs using a single query, which I won't go deep into it. Please see the full paper or come talk to me during the poster session for that. So key takeaways here are we are trying to build this unified framework for optimizing for both extraction and analysis of graphs that are implicitly stored inside of structured data stores. And to do that, we propose a declarative data log-based DSL to do both definitions of graph views as well as queries over those graph views. And we also want to expose a series of APIs to allow users to do very complex analytics over the graphs that they want to analyze. And as I talked about, there's many different challenges and opportunities in doing this. So that's the time I got. Thank you. I'll take any questions.
Thanks, Konstantinos. So, is there a question for this for Konstantinos? Everybody really impressed. So, okay. So you tested this on multiple different database systems, you said, because you observed variance.
That's right, yeah.
Which systems were that again?
We used, sorry about that. We used Postgres, MySQL, and two other databases.
Proprietary ones?
Yeah, proprietary
databases. I see.
Well,
I see you're now already coming forward, so I propose that we thank you if there is no additional question, and we go to the next speaker.
All right. Thank you.
Thanks. So the next speaker is Arnau Prat from UPC Barcelona, and he will talk about graph generation. If we can find the presentation, it's in this folder. Yes. There you go.
It's okay?
Yeah, I can turn it down. PDF.
It's a PDF, yes. Okay. So you can hear me well, I guess. So yes, I'm Arnau. I'm from Barcelona, and this is a joint work with Oracle Labs. And as Peter said, it's about generating property graphs from benchmarking. The motivation, many graph systems nowadays, graph analysis is kind of ubiquitous. So many initiatives of benchmarking these graph systems have appeared. And one of common denominator of these benchmark initiatives is that they need data, they need graphs to run these benchmarks, preferably real ones. And the reason why these want real graphs is because they prefer real graphs. It's because the performance of this system is highly depends on the characteristics of the data they operate on. Right? It's not the same running graph algorithms in a perfectly uniform graph than having a graph with a skewed degree distribution. So, however, this is a problem, which is how do we obtain these real graphs? So we want to obtain them. We face that companies do not want to share them. So you end up having to deal with these guys from the law department, or there's another problem, which is, okay, these graphs do not exist because we want to test our systems in graphs that are significantly larger than the real ones, because we want to put our systems to their limit. So we use the actions that these benchmark designers take in order to train these graphs. So they use synthetic graph generators. However, there is a problem, which is each benchmark, we have seen that each benchmark needs graphs with different characteristics. So it ends up, each benchmark designer, to implementing their own graph processing, their own graph generator, which is a very time-consuming task, and ends up sometimes into reinventing the wheel, because many of these graph generators share many techniques of generating graphs. So we thought that it would be very nice to have a tool where you could just give or provide graph specification or some graph characteristics specification, and this tool then generates the graph that you need for your benchmark. And this is a work in progress that we have been working the last months, which is called DataSynth, that is some kind of synthetic graph generation framework that is available in GitHub, and it's written in Scala and uses Apache Spark. So this is a little bit of the architecture we have. What we want to do is to develop a language that allows you to express this graph specification, that then is sent to it's parsed. This graph specification is parsed, and some kind of execution plan is created. That then, on top of the execution plan, some sort of execution plan, we can do some optimizations for some type of graphs that allows us to create graphs in a more scalable or more accurate. And then this plan is sent into a backend that executes this transparently in a cluster using a well-known cluster runtime. But the first question we make ourselves when developing DataSynth is which are the characteristics that we should be able to reproduce. So in order to answer this question, what we did is to look at the literature and look at what the different benchmarks available and the different graph generators in the literature were actually generating, which graphs and which characteristics they were trying to reproduce. And we realized that there were three main components that were interesting by the community. One where they were interested in generating graphs with different node types and different edge types, with properties at both edges and nodes, and with correlations between these properties. So for instance, I want to generate a person in a social network, and this person has a name which is correlated with its country. Additionally, we realized that benchmarks want a variety structure, because the benchmarks want to see how the different structure of the graphs reflects or affects the performance of the underlying systems. And also because we see that the graphs are in different domains, and graphs from different domains might have different characteristics. And the third thing we realize is that there is some interest in reproducing what we call property structure correlations, which basically means if I am a person, it's more likely that I am from China, it's more likely that I am connected to another person from China than another person from South Africa. So in other words, this means that we want to be able to reproduce what we call joint probability distributions between the properties of the nodes that are connected by an edge. So given this, and last but not least, we want to do this in a scalable way. So what's the problem of this? That having a single algorithm to reproduce all these characteristics and have this degree of flexibility is very costly. So we try to follow a much more simple approach. This is a very high-level overview of how we proceed. So let's assume that we have this simple schema at the top right corner of the slide. So what we do is to split the generation of properties and the generation of a structure at the beginning. So in this case, we generate two property tables. We call property tables, one for the country of the persons and one for the name of the persons. And then what we have is, what we also do in parallel is to generate the structure of the graph that we want to have. Then at a later step, what we do is what we call a node to graph matching. So basically what we say is we assign the different entities we have generated to nodes into the graph in such a way using a technique that allows us to mimic an input joint probability distribution. So I'm running out of time, so I'll be very quick. I think we started a little bit before 10 minutes. But, the first time I looked at it, it was 5 minutes. So in the end, we generate the edges of the properties at the edges. So the approach, the benefit, the main goal of advantage of this approach is that it allows us to reuse existing techniques for graph generation, existing techniques for property generation, and basically also that you just pay for what you get, okay? And the disadvantage is that we rely on a very sophisticated graph matching technique, which is basically, I will skip this slide because I'm running out of time, which is basically consists of creating a block model and reducing the problem of graph matching to a graph partitioning problem. So this means that we can also use existing graph partitioning problems to solve this property to match, property to graph problem. And if you want more details, you can come and talk to me during the poster session. We can further discuss all this and give you more details, and also give you some results about the accuracy we are obtaining with this approach. And finally, I'm ending up. For the next steps now, we want to investigate further and develop further this idea of using graph partitioning for solving this property to graph matching problem. We are pushing hard for having this DSL that will allow you to express these schemas. So far we use JSON, but we want something more elaborate. And also we want to add support for bipartite graphs, which is not currently supported in the implementation we have, but it can be done using the same technique. And in the long term, we would like to have having some sort of data generation as a service. So basically, you can ask for your specification, and then the service provides you with the data you need. And I end up my presentation.
Thank you, Arnau. I think we have time for at most one question. Is there a question?
So just to understand the context, first was LDBC SNB, then there was the Graphalytics, and this is the next step on the LDBC dataset?
I would like to. I mean, my goal is that in the long term, at least have this technique, this tool to have the capabilities to generate the same graphs needed by SNB.
Okay.
This is the long term.
Okay.
Okay. So I would like already Ditran to Bleko to come forward and set up your presentation, and of course thank Arnau for the presentation. It is a fact of life that we are on a time budget, but this is the fact that Arnau couldn't give all the details is of course a great motivation to stop by his poster and to talk with him more about this. So thanks again.
It's okay now?
He has the most beautiful poster of all of us. You can see it when you come there. It is lots of time was put into that. Really? Okay, so we are ready for the next speaker, Dritan Bleko, entropy-based selection of graph cuboids.
Okay. Hello. My name is Dritan, and I am PhD student at Athens University of Economics and Business in Athens, in Greece. This paper called Entropy-Based selection of graph cuboids is a joint work with Yannis Kotidis, my advisor. This is the outline of my talk. I start with the motivation of our work. I describe the graph cube, how is implemented in our framework and how the data are stored in it. I give some main concepts of entropy. We define the external and internal entropy that are used to reduce the graph size and to reveal some interesting irregularities in the data. The experiments at the end show the benefits of our work, and I end with some concluding remarks. So the motivation is that a lot of applications in graph data with attributes at node and edge levels are increased. The interest to manage such data. As a running example, we use a social network with three attributes on nodes: gender, nationality, and profession. We see that the analysts are mostly attracted for irregularities in the data and not so much for uniform data. For this reason, we use entropy to catch such irregularities. The graph cubes enable the exploration of graph data sets by considering all possible aggregations among the node edge attributes, and our techniques aim to select and filter out the subsets, called here cuboids, from very large graph cube by using entropy. Okay. What is the graph cube? Here the graph cube is the Cartesian product of two normal cubes of the starting and ending cube, as we can see in the figure, where dimensions are the grouped attributes used in the analysis, while the cuboid is the result set of a particular grouping on the selected dimensions. We can see here in one example, in the center we have the gender nation cuboid, while on the left we have the gender nation cuboid as a result of the drill down operation from the first cuboid. We can see here that the aggregated edges are split evenly, giving no any interesting correlations. While in the figure on the right, we have the same drill down operation, but with different data, where there we can see some irregularities. For example, we can see that profiles mainly female from USA are mainly related with users from Italy, or males from Italy are related mainly with users from Greece. Such irregularities we want to catch using entropy. Cuboids in the graph cube may be represented also as relations, where here in the figure we can see on the left the cuboid as a graph, while on the right we can see the same cuboid as a relation. We refer to this virtual relation as the dual representation of the cuboid. Okay. As the analysts are attracted mainly to skewed data, we use the information entropy in order to find such information. Information entropy captures the amount of uncertainty that increases when data are uniform and decreases when there are high peaks or irregularities in the data. We distinguish here and define the external and internal entropy. We use mainly the external entropy in order to find, in order to reduce the number of cuboids of the graph cube. Here we define the external entropy of a cuboid as the negative of logarithm of the probability distribution of the cuboid records in its dual representation. We can see the formula in the slide. After that, we can calculate the entropy for the parent cuboid and for the child cuboid, and after that we can calculate the delta entropy, which is the difference between the two external entropies. We define also the external entropy rate, which gives us how informative or how irregularities we add when go from the parent cuboid to the child cuboid. The external entropy rate can help us in order to omit cuboids from the huge amount of cuboids in the graph cube. For example, in this figure, we can see that only 8 cuboids out of 64 remains for a threshold of 10% of external entropy rate in the Twitter dataset that we use in our experiments. We also here define the internal entropy, which in order to gain insight into the distribution of records within a cuboid, because we use here, due to the fact that we consider directed data graphs, we distinguish between two kinds of internal entropies, namely starting internal entropy and ending internal entropy. And we define the starting internal entropy as the conditional entropy of the ending attributes values conditioned from each starting attribute combination of values. We introduce the internal entropy rate, as we can see in the slide, as the fraction between the internal entropy and the maximum possible value of internal entropy. Using this rate, we can select the most prominent trends within a cuboid. Okay, I'm ending.
Your time is running out.
Okay.
1 minute.
We have some experiments here with 3 real data sets, Twitter vContact pockets. This is the characteristics of the data set, and we use for our experiments a cluster using implemented the experiments using Apache Spark. We can see in these experiments how the external and internal entropy reduce the graph size in these 2 slides. And we also compare our method with the iceberg graph cube method. And we can see here that our method gives more information about irregularities comparing with the iceberg graph cube. Okay, here are our conclusions. We present a framework of graph cubes. Also, we address the normal size and complexity of resulting graph cubes, proposing an analysis process that steers users towards interesting parts of the resulting aggregations. We need to find all irregularities in our data, and the experimental results validate the effectiveness of our techniques using entropy. Okay, that's all. Thank you.
Thanks. Thanks, Ritan. Yes, so regrettably there is no time to take your questions here, so I propose that you will take your questions with the poster.
Okay.
And right now we have entered a coffee break. So it's coffee break time. And we have 30 minutes of coffee break. And well, the authors of the papers are wholeheartedly invited to stand by their posters while drinking a coffee. Oh, that's it all went right.
What do you mean? I'm kind of the last talk in this instance. Sure. Yeah, let me do that then.